On March 15, 1944, 15,000 feet above the English countryside, Captain Francis Gabreski pushed his throttle forward and engaged a water injection switch for emergency power. His brand-new P-47 Thunderbolt, equipped with a revolutionary system designed to boost its engine from 2,000 to 2,500 horsepower, stuttered, and began to fail. Below him, German fighters escaped as he struggled to limp back home on reduced power. Across every 8th Air Force base in England, the same nightmare was unfolding. The advanced fuel injection system, intended to give American fighters a decisive edge, was instead destroying their engines. Manifold pressure plummeted, cylinders cracked, and pilots were killed. Military experts declared the problem to be fundamental. You simply couldn't push an air-cooled engine beyond its rated power without catastrophic failure. The laws of physics, they claimed, had unbreakable limits. But in a Connecticut laboratory, junior engineer Frank Walker stared at test results that made no sense. The approved alcohol mixture, widely used to prevent engine knock, wasn't just failing, it was causing it. Walker's data suggested something impossible, a different fuel mixture that could unlock 40% more power from the same engine. The establishment called it suicidal. Walker called it chemistry. Somewhere between these two extremes lay the secret that would allow American fighters to defy everything the Germans thought they knew about the laws of physics. The Rolls-Royce Merlin engines of the escorting Mustangs had already faded into distant specks when Captain Gabreski first felt the tremor in his control stick. At 15,000 feet above the patchwork fields of Cambridge, H's P-47D-10 Thunderbolt stayed in formation with 11 other Republic fighters. Their massive radial engines churned through the thin March air at 2,700 RPM. The manifold pressure gauge read 52 inches of mercury, the normal cruise power for the R-2800 double Wasp engine that powered the Thunderbolt, filling its nose like a mechanical heart. Gabreski had been flying the P-47 for 8 months, racking up victories against the Luftwaffe's finest pilots. But this aircraft was different. Fresh from Republic Aviation's Farmingdale factory, it was equipped with a new modification, anti-detonation injection, or water injection. This system was supposed to transform the reliable but heavy fighter into something that could match the performance of the German interceptors. The radar station at Dover had vectored them toward a formation of Messerschmitt Bf-109s, climbing out of France 30 miles southeast and closing fast. At this altitude, the German fighters had every advantage. They were lighter, more agile, and their engines were optimized for high-altitude combat. But today, Gabreski carried an equalizer the Luftwaffe had never encountered. He reached for the toggle switch beside his throttle, the 6, connected to the pressurized tank behind his seat, which held 15 gallons of isopropyl alcohol mixed with distilled water. Republic engineers had explained the theory during his briefing. Inject this mixture into the supercharger intake during high power settings, and the R-2800 would produce 2,530 horsepower, up from its normal 2,000. 30% more power could mean the difference between chasing German fighters and catching them. The 109s appeared first as glints of sunlight on metal, then as distinctive shapes with elliptical wings and angular tails. Gabreski pushed his throttle to the firewall and flipped the water injection switch. The system was designed to engage automatically above 54 inches of manifold pressure, flooding the supercharger with the alcohol-water mixture, which would prevent the engine knock that typically accompanied emergency power. But instead of the expected surge in power, the engine coughed like a dying man. The manifold pressure gauge, which should have smoothly climbed to 65 inches, instead wavered and began to fall. Engine temperature soared beyond safe limits. Through the cockpit floor, Gabreski felt the irregular vibrations of mechanical failure deep within the engine's 18 cylinders. The RPM dropped despite his throttle position, and worst of all, the distinctive whine of the turbo supercharger turned into an irregular rasp. Lieutenant Bob Johnson's Thunderbolt, flying beside him, was experiencing the same symptoms. Normally aggressive in his pursuit of German fighters, Johnson was now pulling back on his throttle and gesturing frantically at his instrument panel. Across the formation, other P-47 pilots were realizing the same horrifying truth. The miracle system that was supposed to give them a decisive advantage was instead robbing them of power when they needed it most. The German pilots, sensing the Americans' distress, pressed their attack. With their Daimler-Benz 605 engines producing 1,700 horsepower through conventional means, they now had a crushing advantage over the Thunderbolts, which were limping along with only 1,600 horsepower, less than their normal output. Gabreski struggled to keep his crippled fighter in the air, watching helplessly as German fighters tore through his formation. The tactical situation had completely reversed. Instead of dictating the terms of engagement with superior power, the Americans were now forced into a defensive position, their aircraft degraded and vulnerable. 2 more Thunderbolts suffered similar power failures, their pilots urgently reporting engine problems and plummeting manifold pressures. The engagement lasted exactly as long as it took for the Americans to realize their miracle system had turned into a disaster. 12 minutes later, the Luftwaffe had escaped without a single loss, while 3 P-47s limped home on partial power. Their water injection systems were switched off, and their pilots nursed engines that coughed and sputtered erratically. Gabreski managed to coax his Thunderbolt back to IAF Steeple Morden, keeping the throttle at reduced settings while listening to the irregular rhythm of cylinders failing to fire in proper sequence. On the ground, Master Sergeant Mike Quirk removed the cowling panels from Gabreski's aircraft and immediately diagnosed the problem. Cylinder number 14 showed severe signs of detonation, the kind of spontaneous combustion that could destroy an engine in moments. The spark plug electrodes were eroded, and the cylinder head had heat stress fractures, while black residue coated the intake ports. This wasn't random mechanical failure. It was systematic destruction. Within hours, similar reports came flooding in from across the 8th Air Force's fighter bases. At Boxstead, Debden, and Lineham, ground crews were removing cylinders from newly modified P-47D-10S that had been equipped with a water injection system. The pattern was unmistakable. Engage the ADI at high power settings, and the engine began to destroy itself from within. Colonel Hubert Zama, commander of the 56th Fighter Group, grounded his entire squadron for further investigation. At Debden, the 4th Fighter Group followed suit. By evening, nearly 200 of the Army Air Force's most advanced interceptors sat idle on their hardstands. Their revolutionary power systems had been deemed unsafe for combat operations. In his debriefing report, Gabreski wrote with characteristic precision, "Water injection system caused severe engine roughness and power loss at 63 inches manifold pressure. The system appears to promote rather than prevent detonation. Recommend immediate investigation." He refrained from mentioning his personal suspicion that somewhere between Republic Aviation's design desk and Pratt and Whitney's machine shops, a fundamental miscalculation had turned a most promising technical advantage into a potentially war-losing liability. The miracle that was meant to give American fighters the upper hand over the Germans had instead made them vulnerable to conventional German fighters. And no one could yet understand why. On March 20th, 1944, the emergency conference at Wright-Patterson Army Airfield convened at 0800 hours. Representatives from every organization involved in American fighter engine development gathered around a mahogany table. Colonel Benjamin Chidlaw, head of the Fighter Projects Office, sat at the head of the table, surrounded by the most experienced aeronautical engineers in the United States. To his left, Leonard Hobbs from Wright Aeronautical Corporation spread technical drawings across the table's polished surface. To his right, senior engineers from Pratt and Whitney arranged folders filled with test data and failure reports. The consensus emerged quickly, solidifying like concrete setting in cold weather. Dr. Samuel Harron, the British-born combustion expert who had shaped American engine design for 2 decades, spoke with the authority of accumulated knowledge. The R-2800 Double Wasp, he explained, was already operating at the absolute limits of metallurgical and thermodynamic capabilities. 18 cylinders, displacing 284 cubic inches, running at 2,700 RPM, and producing 2,000 horsepower from air-cooled aluminum and steel. This was a pinnacle of piston engine development. The mathematics were irrefutable. A compression ratio fixed at 6.65 to 1, cylinder head temperatures that couldn't exceed 500 degrees Fahrenheit without warping aluminum castings, and manifold pressure limited to 52 inches of mercury to prevent detonation. These weren't arbitrary limitations, but physical laws as absolute as gravity or thermodynamics. Major Harold Neely from Wright Aeronautical presented failure analyses that confirmed every assumption. The destroyed cylinders from England showed classic detonation damage. Electrodes burn away by temperatures exceeding 3,000 degrees Fahrenheit. Aluminum pistons with holes melted clean through cylinder walls, scored by metal fragments traveling at supersonic speeds. This was a consequence of engineers trying to exceed nature's limits. This was what happened when wartime pressures pushed technology beyond reasonable boundaries. The procurement officers nodded in satisfaction, their conservative instincts vindicated. Colonel Robert Harper from Material Command had opposed a water injection program from the beginning, arguing that field modifications introduced too many variables for reliable operation. Combat aircraft needed systems proven through thousands of hours of testing, not experimental modifications rushed into production. The engine failures in England had proven his point. Leonard Hobbs unrolled a cross-sectional drawing of the R-2800 combustion chamber and traced the source of the problem with mechanical precision. Fuel and air entered through intake valves, compressed by aluminum pistons rising in steel cylinders, ignited by precisely timed spark plugs. Under normal power settings, combustion proceeded smoothly from the spark plug outward, forming an expanding flame front. But when pressure and temperature exceeded design limits, spontaneous ignition occurred simultaneously throughout the mixture. Instead of a controlled expansion pushing the piston down, a violent explosion hammered it, forces that no mechanical system could withstand. The isopropyl alcohol mixture currently used in the water injection system had an octane rating of 118, higher than aviation gasoline, theoretically sufficient to prevent premature ignition. However, theory and practice diverged when aluminum castings were subjected to temperatures beyond their design limits and compression ratios near the detonation threshold. The alcohol simply could not overcome the fundamental physics of internal combustion. Dr. Heron emphasized a mathematical certainty with numbers that left no room for debate. Cylinder pressure at maximum power reached 800 pounds per square inch, and the temperature inside the combustion chamber soared to 2,200 degrees Fahrenheit. Heat rejection through the cylinder cooling fins amounted to 42,000 BTUs per hour. These figures represented the absolute limit of air-cooled engine performance, established through decades of research and validated by thousands of hours of testing. The younger engineers from Pratt Whitney, including Bill Claus and the junior chemist Frank Walker, listened with growing frustration as the senior experts dismantled their hopes for a technical solution. Walker had submitted preliminary data suggesting that different alcohol formulations might behave differently under extreme conditions, but his research was dismissed as mere laboratory speculation, disconnected from engineering reality. Methanol and ethanol might show promising characteristics in controlled tests, but in the field, operations required proven, reliable, and available materials. Colonel Harper explained the procurement logic with devastating clarity. Isopropyl alcohol were produced in large quantities by pharmaceutical companies, available through existing supply chains, and compatible with rubber seals and aluminum fittings throughout the injection system. Switching to alternative alcohols would require months of testing, new production contracts, modified storage procedures, and retraining of maintenance personnel. The war would not wait while engineers pursued theoretical improvements. The meeting concluded with unanimous agreement to suspend the water injection program and return the R-2800 engine to its proven 2,000 horsepower rating with conventional fuel systems. American fighters would accept their performance disadvantage rather than risk catastrophic mechanical failure in combat. As the participants gathered their papers to leave, Frank Walker remained seated, staring at data everyone else had dismissed. His lab tests showed octane ratings that contradicted accepted wisdom: methanol at 133, ethanol at 129, and pure water with an infinite octane rating, because it couldn't burn at all. But these numbers meant nothing unless they could be translated into engines that functioned in combat. The conventional wisdom had spoken with absolute authority. Physics imposed limits that engineering could not overcome, and prudent design required accepting those limits rather than challenging them. The water injection system would be abandoned, and American fighters would remain at a disadvantage, relying on technologies that work reliably, though not optimally. Walker closed his notebook, knowing that mathematical certainty and engineering reality sometimes diverge in ways senior experts couldn't imagine. Bill Claus arrived at IAF Steeple Morton on March 28 with a canvas bag and determination bordering on insubordination. The official directive from Wright-Patterson had been clear: suspend all water injection testing and return the P-47 fleet to standard configuration. But Claus had spent the Atlantic crossing studying Frank Walker's laboratory data, and the numbers suggested possibilities that contradicted every expert opinion he had heard. Master Sergeant Mike Quirk met him at the hard stand where Gabreski's damaged Thunderbolt sat, its cowling panels removed to expose the wounded R-2800 like a patient ready for surgery. Quirk had been maintaining radial engines since before Pearl Harbor, and his practice I could read mechanical distress from the carbon deposits and metalware patterns. This particular engine told a story of violence, with cylinders hammered by explosions instead of powered by controlled combustion. Claus examined the destroyed components with the methodical precision of a detective studying crime scene evidence. Piston number 14 showed a hole melted clean through its aluminum crown. The intake valve was warped beyond specification. Carbon deposits coated surfaces that should have been clean, but most telling were the spark plug electrodes, eroded into irregular shapes that spoke of temperatures far exceeding normal combustion limits. Walker's theory focused on molecular behavior that occurred faster than human perception could follow. During the few milliseconds between spark ignition and piston movement, alcohol molecules broke apart under extreme temperature and pressure. Isopropyl alcohol, the approved mixture, degraded into compounds that actually promoted spontaneous combustion rather than preventing it. But methanol and ethanol behaved differently, maintaining their anti-detonation properties even under the savage conditions inside a combat-loaded R-2800. The challenge was proving this theory without official authorization or adequate testing equipment. Claus convinced Quirk to prepare a single P-47 for testing. For clandestine trials, using maintenance procedures that appeared routine, Walker's radical chemistry was implemented. They drained the isopropyl alcohol mixture from the injection tank and replaced it with methanol, purchased from a Cambridge chemical supply company, mixed 50/50 with distilled water. Lieutenant Colonel Francis Gabreski volunteered his aircraft for the unauthorized test despite explicit orders grounding the water injection system. His motivation was personal. German fighters had escaped during the March 15th engagement specifically because his Thunderbolt lacked the power to pursue them effectively. If Walker's mixture could restore the performance advantage, Gabreski was willing to risk court-martial proceedings. Initial ground tests revealed immediate differences that contradicted every expectation. Where isopropyl alcohol had caused rough running and power loss, the methanol mixture produced smooth acceleration through the entire power range. Engine temperatures remained within normal limits even at 65 inches of manifold pressure. Most dramatically, the characteristic whine of the turbo supercharger maintained its steady pitch instead of fragmenting into the irregular rasp that had signaled mechanical distress. Claus monitored the engine instruments while Quirk adjusted fuel flow and injection timing. Manifold pressure climbed smoothly from 52 inches to 65 inches without the hesitation that had plagued previous attempts. Cylinder head temperatures, instead of spiking beyond safe limits, actually decreased as the methanol-water mixture absorbed combustion heat and prevented the hot spots that triggered detonation. The breakthrough came during a high-power engine run that would have destroyed the power plant with isopropyl alcohol injection. Gabreski pushed the throttle to the maximum emergency setting, 68 inches of manifold pressure at 2,800 RPM. The R-2800 responded with authority, producing 2,800 horsepower instead of the normal 2,000. Through his headset, Claus heard the deep-throated roar of an engine operating beyond its rated capacity without mechanical distress. The performance numbers validated Walker's most optimistic projections. The rate of climb increased from 2,800 feet per minute to 3,800 feet per minute. Time to 15,000 feet dropped from 6.2 minutes to 4.1 minutes. Most significantly, top speed at 25,000 feet increased from 425 miles per hour to 465 miles per hour, faster than any German fighter at equivalent altitude. Word of the successful test spread quickly through the 56th Fighter Group with a velocity of classified information that everyone needed to know. Squadron commanders who had witnessed their pilots struggle with underpowered aircraft suddenly faced the possibility of technical superiority over the Luftwaffe. But implementing Walker's mixture required circumventing official channels and risking careers on unproven chemistry. Major David Schilling, the group's most experienced test pilot, convinced Colonel Zampi to authorize a single demonstration flight using the modified injection system. On April 3rd, Schilling took Gabreski's Thunderbolt to 30,000 feet and engaged a water injection during a high-speed run designed to test Walker's theory under combat-simulated conditions. The results exceeded every expectation. Schilling's P-47 accelerated from 400 miles per hour to 480 miles per hour in level flight, then climbed at full power without the engine roughness that had plagued previous isopropyl alcohol trials. Ground observers tracking the flight reported speed measurements that seemed impossible, a Thunderbolt maintaining 465 miles per hour at 28,000 feet while climbing at over 3,000 feet per minute. Schilling's radio transmission crackled with excitement, his professional composure momentarily slipping. "This thing climbs like a rocket and runs like a scolded cat." Whatever Walker put in that mixture, it turned the Jug into a completely different airplane. The flight data confirmed performance improvements that transformed the P-47 from a capable but heavy interceptor into a fighter that could dominate any opponent through superior power and climb rate. By evening, mechanics throughout the 56 fighter group were quietly draining isopropyl alcohol from injection tanks and refilling them with Walker's methanol mixture. The transformation was accomplished without official authorization, documentation, or oversight, a grassroots technical revolution driven by combat necessity rather than bureaucratic approval. Frank Walker's chemistry had proved itself where theories mattered most, in the three-dimensional arena of aerial combat, where performance differences measured in seconds determined whether pilots lived or died. Colonel Hubert Zampi made a decision that would either validate Frank Walker's chemistry or destroy the most successful fighter group in the European theater. On April 7, 1944, he authorized the conversion of every P-47 in the 56 fighter group to the unauthorized methanol water mixture, gambling 48 aircraft and their pilots on the laboratory calculations of a junior engineer 3,000 miles away. The logistics required deception that bordered on mutiny. Master sergeants throughout the group coordinated their efforts like conspirators planning a coup, draining approved isopropyl alcohol from injection tanks during routine maintenance. During maintenance periods, isopropyl alcohol was drained from the injection tanks and replaced with methanol purchased from civilian suppliers. Technical orders were ignored. Procurement procedures were bypassed. Quality control inspections were carried out by mechanics who knew exactly what violations they were covering. Captain Robert Johnson understood the magnitude of the risk as he walked around his P-47 during the pre-flight inspection on April 8th. If Walker's mixture failed during combat, the engine would destroy itself at the moment when maximum power was most critical. During emergency climbs, high-speed pursuits, or desperate attempt to escape superior numbers of enemy fighters, mechanical failure at 25,000 feet over Germany meant capture or death with mathematical certainty. The mission briefing had been routine until Colonel Zampi announced a tactical modification. The 56 fighter group would escort B-24 Liberators to Brunswick, penetrating 300 miles into German airspace, where the Luftwaffe concentrated its most experienced pilots and advanced aircraft. But instead of the conservative fuel management that had characterized previous operations, pilots were now authorized to use water injection at full combat power whenever tactical advantage required maximum performance. Johnson led Red Flight at 26,000 feet, flying loose formation with 3 other Thunderbolts while scanning the crystalline air above the bomber stream for the glint of metal that would announce German interceptors. The Liberators droned steadily eastward at 160 miles per hour, their contrails marking their position for any enemy pilot within 50 miles. Defending them required constant vigilance and the ability to transition instantly from escort formation to combat maneuvering. The attack developed with textbook precision at 11:47 hours. 20 Focke-Wulf 190s dropped out of the sun from 30,000 feet, using altitude and surprise to achieve the overwhelming advantage that German tactics required. Their radial engines, WWII producing 1,700 horsepower, gave them performance margins that had dominated every previous engagement with standard P-47s. Johnson rolled inverted and pulled through a split-S maneuver, pointing his Thunderbolt directly at the attacking Germans. At 25,000 feet, with his airspeed building through 300 miles per hour, he reached for the water injection switch that had been disconnected for 3 weeks following the March disasters. This time, instead of isopropyl alcohol that would destroy his engine, methanol and distilled water flowed into the supercharger intake. The transformation was immediate and violent. Johnson's R-2800 engine, which had been producing 2,000 horsepower, suddenly generated 2,800 horsepower with a sound like controlled thunder. The Thunderbolt accelerated as if launched by catapult, its massive bulk shedding the sluggish characteristics that had defined every previous combat engagement. Manifold pressure climbed to 68 inches of mercury. Engine temperature remained within normal limits. The RPM increased to 2,800 without mechanical distress. Johnson's tactical situation reversed completely within 30 seconds. Where German fighters had previously held decisive advantages in climb rate and acceleration, his Thunderbolt now possessed superior performance in every regime of flight. He pulled into a climbing turn that would have been impossible with standard power settings, positioning himself above the Focke-Wulfs despite their initial altitude advantage. The physics of aerial combat changed with Walker's chemistry. German pilots, who had grown accustomed to American fighters that climbed slowly and accelerated reluctantly, now face opponents that could outrun and outclimb their own aircraft. The BMW 801 engines in the Focke-Wulfs, which had represented technological superiority for 2 years, were now producing 400 fewer horsepower than the modified R-2800s. Johnson engaged a leading Focke-Wulf at convergence angles that would have been suicidal with normal P-47 performance. His closing speed exceeded anything the German pilot had experienced in previous combats with Thunderbolts. The .50 caliber machine guns concentrated their fire through a target area that dissolved under the impact of armor-piercing and incendiary bullets traveling at 2,800 feet per second. The German aircraft disintegrated in a flash of orange flame and black smoke, its pilot having no opportunity to evade or return fire. Johnson pulled through a vertical climb that gained 3,000 feet in less than 30 seconds, then rolled over to attack the formation's second element. His wingmen, flying identical aircraft with identical modifications, were experiencing the same performance transformation. Lieutenant Eugene Roberts destroyed 2 Focke-Wulfs during a high-speed diving attack that reached 560 miles per hour, faster than any German fighter could achieve in level flight. Captain Gerald Johnson climbed vertically through the German formation, using his superior power-to-weight ratio to position himself for deflection shots that were impossible with conventional performance. The engagement lasted 18 minutes and resulted in a complete tactical reversal. The 56 Fighter Group destroyed 11 German fighters without loss, demonstrating performance advantages that contradicted 2 years of combat experience. German pilots, who had learned to exploit American weaknesses, suddenly faced opponents that controlled every aspect of aerial maneuvering. Major Hermann Graf, commanding the German formation, Major Hermann Graf transmitted a combat report that reached Luftwaffe headquarters within hours. American fighters demonstrated impossible performance characteristics. P-47s climbed and accelerated beyond known specifications. He recommended an immediate investigation into enemy technical modifications. His description of Thunderbolts that could outrun Focke-Wulf 190s and outclimb Messerschmitts was initially dismissed as combat exaggeration. Johnson's post-flight debriefing documented the transformation with such precision that it satisfied both engineers and tacticians. Water injection had functioned flawlessly throughout the combat, providing emergency power whenever needed, with no mechanical issues. Engine temperatures remained normal, and performance exceeded all predictions. The methanol-water mixture had turned the P-47 from a defensive interceptor into an offensive weapon that could dominate any opponent. Frank Walker's chemistry had been validated in the ultimate laboratory, aerial combat, where theoretical calculations determined the difference between victory and defeat, survival and death. The transformation of the 8th Air Force began with a single teletype message transmitted from IAF Steeple Morden at 2,100 hours on April 8. Colonel Zampe's combat report, classified secret, and marked for immediate distribution to all fighter commands, contained performance data that contradicted every assumption about American fighter capability. P-47s had achieved climb rates of 3,800 feet per minute. Top speeds had reached 470 miles per hour at altitude. Most significantly, not a single engine had failed during maximum power operations, which would have been catastrophic with the original injection system. Within 48 hours, mechanics at Debden, Boxted, and Lyon were quietly implementing Walker's methanol mixture, despite the absence of official authorization. Technical sergeants, who had witnessed months of engine failures, suddenly found themselves installing a system that worked exactly as promised. An underground network of maintenance personnel shared information through channels that bypassed the normal command structure, driven by combat necessity rather than bureaucratic approval. Lieutenant Colonel Don Blakesley, commanding the 4th Fighter Group at Debden, authorized a conversion of his entire P-51 Mustang squadron after consulting with engineers who had studied the chemical differences between alcohols. The Packard-built Merlin engines in his fighters required different injection pressures and timing, but the fundamental chemistry remained the same. Methanol prevented detonation, while water absorbed combustion heat, allowing manifold pressures that would destroy engines using conventional fuels. By May 1st, every American fighter squadron in England was using Walker's mixture. The results were reflected in statistics that redefined aerial warfare. American fighter losses dropped by 37%. German fighter losses increased by 52%. Mission abort rates due to mechanical failure dropped to near zero. Most dramatically, the tactical balance in European skies shifted decisively toward American forces for the first time since the daylight bombing campaign began. The Luftwaffe response revealed the magnitude of the transformation. Major General Adolf Goland, commanding German fighter forces, issued emergency tactical bulletins warning his pilots that American fighters had been fundamentally upgraded. The familiar performance characteristics that German pilots had learned to exploit no longer applied. P-47s could no longer be outrun by diving away. P-51s could no longer be escaped by climbing to maximum altitude. American fighters had become predators instead of prey. Frank Walker received official recognition through channels he had never imagined. Lieutenant General Carl Spaatz, commanding all American air forces in Europe, personally reviewed the combat data and authorized the immediate implementation of Walker's system throughout the theater. The junior engineer, whose laboratory work had been dismissed by senior experts, found himself summoned to Wright-Patterson Field for consultation with the Army Air Force's highest leadership. The technical validation came through exhaustive testing that confirmed Walker's molecular theory. The Chemical Warfare Service analyzed fuel samples from combat aircraft and discovered that methanol maintained its anti-detonation properties under conditions that degraded isopropyl alcohol into compound promoting spontaneous ignition. Water injection, instead of being a desperate expedient, was actually superior to purely chemical solutions because it addressed both detonation and thermal management simultaneously. Production facilities throughout the United States began manufacturing methanol water injection systems using Walker's specifications. The Pratt Whitney plant in East Hartford converted an entire production line to mixing equipment capable of producing 10,000 gallons per day. Shell Oil Corporation developed storage and transportation procedures that maintained the precise 50-50th ratio essential for optimal performance. By summer, the mixture that had been assembled in secret by English mechanics was flowing through official channels. Supply channels to every American air base in the European theater were established to distribute the methanol water mixture. The tactical implications stretched far beyond individual aircraft performance. American bomber formations, previously limited to altitude where fighter escorts could offer effective protection, now began operating at 35,000 feet, a height where German interceptors struggled to maintain combat effectiveness. Deep penetration missions that had once required massive fighter support could now be conducted with smaller escort forces that possessed overwhelming individual superiority. German technical intelligence services captured damaged American aircraft and uncovered the injection system that was revolutionizing aerial combat. Their analysis revealed sophisticated engineering that had somehow solved the fundamental issue of extracting additional power from air-cooled engines without causing catastrophic failure. Within months, German manufacturers began developing their own methanol water systems, designated MW50, for installation in Focke-Wulf 190s and Messerschmitt 109s. However, German implementation came too late to influence the war's outcome. American production advantages had already established air superiority through numbers, and Walker's chemistry had created technological superiority that German manufacturing could not match. By the time the Germans received their own injection systems, American forces were already operating from captured airfields in France and preparing for the final assault on German industrial targets. The human cost of Walker's discovery was measured in lives saved rather than lost. American pilot casualties decreased sharply as their aircraft gained performance margins necessary to dictate the terms of combat engagements. German pilot losses increased as their tactical advantages vanished. What had once been a war of mutual attrition now became a systematic dismantling of German air power through technological superiority combined with industrial capacity. Walker himself returned to the Pratt Whitney laboratory in Connecticut, where he continued developing combustion chemistry to power the next generation of American aircraft. His wartime breakthrough laid the foundation for turbine engine development, rocket propulsion research, and eventually the chemical systems that would propel spacecraft to the moon. The final irony emerged from German technical documents captured after the war's end. Luftwaffe engineers had understood the theoretical basis for alcohol injection years before American implementation, but their conservative approach to combat modifications had prevented field testing. German expertise in chemistry and metallurgy might have led to superior results if applied with the same urgency that characterized American development. Instead, their methodical approach to technical validation was overwhelmed by Walker's willingness to implement unproven theories under combat conditions. The laws of physics had not been defied. Rather, they had been revealed by a junior engineer whose laboratory work fundamentally transformed the equation of aerial warfare.